Good morning, all. I am Reenu Rajan of first semester SCCM SNIT ADO. Today I am here to discuss about the topic potentiometer bridges or circuits. First of all, we should know what is a potentiometer. Potentiometer is a variable resistor that has three terminals, two fixed terminal and one variable terminal. In this device, current flow is controlled by varying the resistance manually. Potentiometer does the function of an adjustable voltage divider. Applications of potentiometer. Potentiometer can be used as voltage divider to measure the voltage across given circuit, to compare the EMF of a battery cell with a standard cell, to measure internal resistance of a battery cell, and audio control. The potentiometer circuit is given below. It consists of mainly two resistors. It is represented as R1 and R2 and one capacitor and battery with voltage V. The output voltage across two terminals is denoted as E. In this potentiometer topic, we have to find out the terms sensitivity, range and power dissipations, etc. So first of all, we should know the potential divider formula. In the first figure, it is shown that there is a high resistance wire, and in the second figure shows that there is total voltage V, and the voltage across resistor R1 is denoted as V1 and voltage across resistance R2 is denoted as V2. Therefore, V1 is equal to V into R1 divided by R1 plus R2. Similarly, V2 is equal to V into R2 divided by R1 plus R2. Here is also an example in the third figure. V is equal to 2, that is V into 70, that is R1 divided by total voltage 30 plus 70, that is R1 plus R2. Therefore, we get V is equal to 1.4 volt. So, the first step is the open circuit voltage E is equal to, E means output voltage, E is equal to R1 divided by R1 plus R2 into V. R is equal to R2 by R1. Therefore, it can be converted to a short form such that E is equal to 1 by 1 plus R into V. When R1 increases by delta R1 and R2 by delta R2, then the output voltage becomes E plus delta E is equal to R1 plus delta R1 divided by R1 plus delta R1 plus R2 plus delta R2 into V. Delta E is equal to R1 plus delta R1 divided by R1 plus delta R1 plus R2 plus delta R2 minus R1 by R1 plus R2 into V. The above equation is rearranged as delta E is equal to R divided by 1 plus R the whole square into delta R1 by R1 minus delta R2 by R2 into 1 minus eta into V, where R is equal to small r is equal to R2 by R1. Eta is equal to 1 minus 1 by 1 plus 1 by 1 plus R into delta R1 by R1 plus R into delta R2 by R2. Eta is the non-linear term. If R1 is equal to Rg, which means resistance 1 is equal to the gauge resistance Rg and R2 is equal to Rb. Resistance R2 is equal to ballast resistance Rb, so that delta R1 equal delta Rg and delta R2 is equal to 0. Therefore, eta equal 1 minus 1 by 1 plus 1 by 1 plus R into delta Rg by Rg. The above equation, which can again rearranged as eta is equal to 1 minus 1 by 1 plus 1 by 1 plus R into F epsilon, where F is the gauge factor and epsilon is the strain. Eta can be written as eta is equal to 1 minus 1 by 1 plus x. X is equal to f epsilon by 1 plus r. Eta is equal to 1 minus 1 plus x the whole raised to minus 1. According to binomial expansion, eta becomes 1 minus 1 plus x minus x square plus x cube minus x raised to 4 plus etc. is equal to x minus x square plus x cube minus x raised to 4 plus etc. Here is a graph shown. In the x-axis, it is represented as mu, strain, and in y-axis, non-linearity terms, eta is represented. The range of potentiometer circuits depends upon error which can be tolerated due to the non-linearities introduced in the circuit. From the figure, the non-linear term is given as a function of various values of R. It can be seen that error introduced by the non-linearity term is sufficiently small to be negligible for strengths below 1%. Increasing the value of R decreases the error due to circuit non-linearity. Sensitivity. Sensitivity of potentiometer is written by the letter SC. SC is equal to delta E by epsilon. Substitute the value of delta E values. Therefore, SC is equal to R divided by 1 plus R the whole square into delta R1 by R1 minus delta R by R2 by R2 into V by epsilon when eta less than 1. Also, if R1 equal Rg, that means resistance 1 is equal to gauge resistance and delta R1 equal delta Rg, R2 equal B and delta R2 equal 0, then we get SC is equal to R by 1 plus R the whole square into delta Rg by Rg into V by epsilon. Delta Rg by Rg can be written as F into epsilon. F is equal to gauge factor. Epsilon and epsilon is strain. Therefore, SC is equal to R by 1 plus R the whole square into F epsilon into V by epsilon. Therefore, SC is equal to R by 1 plus R the whole square into FV. This equation shows that the circuit sensitivity depends upon the ratio R and supply voltage V. V is equal to IR according to Ohm's law. Therefore, V is equal to Ig into Rg plus Rb. Ig Rg into 1 plus R. It can be also written in terms of power dissipation and resistance. Therefore, V is equal to root of Pg Rg into 1 plus R. Sc is equal to R by 1 plus R into F into Ig Rg. Again, the values of V and Ig can be substituted. Therefore, Sc is equal to R by 1 plus R into F into root Pg Rg. Pg is the power dissipated by the gauge. This equation shows that the circuit sensitivity depends upon the values of R by 1 plus R and F into root Pg Rg. The sensitivity increases as the value of R by 1 plus R increases. Values of R about 9 are commonly used and circuit efficiency is normally about 90%. Temperature compensation. Let R1 be the active gauge and R2 be the dummy gauge. Let R1 epsilon and R1 delta R1T be the changes in the resistance of gauge R1 due to strain and temperature respectively. Therefore, delta R1 by R1 equal delta R1 epsilon by R1 plus delta R1T by R1. If delta R2T be the change in resistance due to temperature of gauge, then delta R2 by R2 equal delta R2T by R2. In resistance 2, that is in R2, there is only the effect of temperature and no effect of strain. Delta E equal R by 1 plus R the whole square into delta R1 epsilon plus delta R1T by R1 minus delta R2T by R2 into 1 minus eta into V. If R1 equal R2 equal G, then delta R1 T equal to delta R2 T, and temperature terms cancel out and we get delta E is equal to 1 by 4 into delta R1 epsilon by R1 into 1 minus eta into V, 1 by 4 into delta R1 epsilon by R1 can be written as F epsilon, 1 minus eta into V. Therefore, we can substitute in terms of Ig, Rg, Pg and Rg. Therefore, at last we get the equation delta E is equal to 1 by 2 into F epsilon into root of Pg Rg. Calibration. Calibration of potentiometer circuit may be achieved either placing shunt resistance across the strain gauge or ballast resistance R2. For the first method shown in figure 5.42, the equivalent resistance of the strain gauge becomes. Here there are two methods. In first method, we can place a shunt resistance across the strain gauge. In the second method, the shunt resistance is placing across RB, that is ballast resistance. Therefore, equivalent resistance RE equal RG RSH by RG plus RSH. Therefore, delta RG is equal to RG minus RG RSH by RG plus RSH. By rearranging terms, delta RG is equal to R square G by RG plus RSH. Delta RG by RG equal delta RG by RG plus RSH. Delta RG by RG can be written as R epsilon E. We get the shunt resistance RSH is equal to Rg into 1 minus F epsilon E by F epsilon E. F epsilon E, in F epsilon E term, epsilon E is the equivalent strain. Thank you.